So Europe is on fire right now. Literally. Major wildfires have displaced hundreds of thousands of people across France and Spain, and even the UK is seeing a spate of devastating fires. Aside from those fires, the UK saw over 2,700 excess deaths as a result of the heat waves in May and June alone. Other European countries such as France, Germany, Spain, and the Netherlands have experienced similar spikes in excess deaths. If the periodic, rather unhinged comments some of my videos get are anything to go by, climate change is a topic drowning with misinformation. Now, if the overwhelming body of scientific evidence can't convince someone, I doubt my video will. But for the rest of the world, I know many of you have questions, and I'm here to try and provide some answers. Hi, I'm Dr. Eleanor Tufnell, an environmental scientist, and the climate topic I'm covering today is whether or not it's actually possible to reverse climate change. I'll be talking you through Stratospheric Aerosol Injection, or SAI, which may be considered the most effective solar radiation modification technique, or SRM, that may offer the best option for rapidly reducing global temperatures. I'll explain what it is, how it works, the challenges facing it, and the potential benefits it may offer. I will be keeping things relatively simple and accessible, so if you're looking for an advanced tutorial on the chemistry and physics involved, this may not be the best video for you. Though do check out the research papers listed in the description, as you may find these very useful. However, if what you want is a whistle-stop tour of the topic that leaves you informed but doesn't make you feel patronised, I aim to please. How does it work? Now, the chemistry and physics involved in stratospheric aerosol injection, SAI, is of course rather complex, but the basic principle is actually very simple. The idea arose from observations of the aftermath of major volcanic eruptions, such as 1991's Mount Pinatubo eruption, which spewed massive quantities of reflective particles into the stratosphere. Such major eruptions are often followed by a period of cooler temperatures. The mechanism for this is a global dimming. The reflective particles scatter incoming solar radiation, reflecting it back into space. The result is surface cooling of the planet, as less solar radiation reaches the surface. However, as these particles can also absorb radiation from the Earth, this can lead to a warming in the lower stratosphere, which carries its own risks. So a balance between these two effects is crucial. There are, however, a lot of factors at play, which determine which effect is dominant and how strong it is. These include the size of aerosol particles, their optical properties, their chemical composition, what height they were injected, and their spatial distribution. Quick note, the term aerosol has several meanings, but here refers to fine, solid particles or liquid droplets, which are suspended in gas. Different chemical compounds will determine what chemical processes their presence in the stratosphere will trigger or inhibit. And the effect can be substantial. The Mount Pinatubo eruption is estimated to have resulted in a 0.3 to 0.5 degree Celsius reduction in global mean temperatures for the 2 years following the eruption. During the eruption, roughly 20 million tons of sulfur dioxide were propelled into the stratosphere. Using this as a guide, it could be estimated that in order to achieve a global mean reduction of temperature of 1 to 2 degrees Celsius, we would need to inject several million tons of sulfur dioxide or equivalent yearly to achieve and maintain the same results. Volcanic eruptions can provide valuable information on how aerosol particles are distributed, how long they remain in the atmosphere, and the impact on the climate. And as eruptions have occurred during different seasons and at different latitudes, this can help our understanding of how these factors affect climate response and aerosol dispersal. However, due to their sporadic and unpredictable nature, volcanoes can only answer some of our questions on the topic. For the rest, we are largely reliant on model-based studies, which may simulate a variety of factors, such as using different aerosols, different quantities, different locations for their release, different release methods, and different release altitudes. How would it be done? But if you actually wanted to implement SAI in the real world, how would you do it? Well, a variety of methods have been proposed. How efficient SAI is at cooling and what side effects and dangers are most likely depend on what is injected, where it is injected, and when it is injected. For example, injecting aerosols at a higher altitude and in locations that feature the most favourable stratospheric transport, it is most efficient. One report estimated that if injection took place at 19 to 20 kilometres altitude, it had only 61% of the cooling efficiency seen when injecting at 23 or 25 kilometres altitude. Though as different models and scenarios will show different things, it can be hard to pin down the most efficient strategy. From what we know so far, injection high up seems to be the most efficient. At present, suggested options for SAI injection are at high altitudes, such as 20 kilometres, which is more efficient as particles stay up longer, but is also more expensive as most commercial aircraft do not fly this high, so specially designed aircraft would need to be built and maintained. Injection at lower altitude, around 13 kilometres, closer to the poles where the tropopause occurs at a lower altitude. The tropopause is the boundary layer between the troposphere, the layer of the atmosphere closest to the ground, and the stratosphere, the second layer of the Earth's atmosphere, where the ozone layer is located. And this layer's altitude varies both by season and latitude. Injecting lower would allow commercially available aircraft to deliver aerosols, but would require substantially more aerosols and be overall less efficient. More aerosols would also increase any negative side effects. Injecting at very high altitudes, 50 kilometres, would be extremely efficient at cooling and avoid warming the lower stratosphere, thus avoiding or mitigating impacts to atmospheric circulation, stratospheric ozone and water vapour. However, this would require rockets to deliver the aerosol and would thus be logistically challenging and very expensive. A lot of research is being done on the effect different latitudes and longitudes would have on the efficiency of SAI. So far, this research indicates injection at the tropics provides the most efficient cooling. Atmospheric circulation is also something that needs to be taken into account when predicting the spatial distribution of aerosols and how long they will remain in the stratosphere. The longer they can remain there, the less often they need to be replenished. It would also be necessary to balance SAI between hemispheres to provide global cooling and mitigate any impacts from changes to the hemisphere's temperature gradients. I won't go into details about stratospheric circulation here, but transport of air between hemispheres is slow and will also need to be taken into account. SAI would also require reliable methods for producing the necessary aerosols at uniform size and would need the means to deploy them. That could include high-altitude aircraft or balloons, but it would also need to include ships if the launch sites were at sea. Which aerosols could we use? The first aerosol considered is, of course, sulfur dioxide, because we already know it works and have real-world analogues, volcanoes, to give us a sense of how well it will work. However, while sulfur dioxide is effective, it also carries a number of risk factors that make it less desirable as a candidate for large-scale SAI projects. Sulfur dioxide absorbs quite a bit of terrestrial radiation and thus can warm the stratosphere. It can negatively impact stratospheric ozone recovery, atmospheric circulation, and there are harmful effects of sulfur dioxide deposition, think acid rain. However, sulfur dioxide is not the only possible candidate. Other aerosols could potentially be more chemically inert, impacting stratospheric ozone less. They might also absorb less solar radiation and thus mitigate the heating of the stratosphere. A large number of possible candidates are being explored, including calcium carbonate, aluminium oxide, titanium oxide, and even diamond dust. Some companies are looking at natural compounds, though most are pretty cagey about precisely what these are, presumably because they haven't been patented yet. Many of these compounds have shown considerable promise in model studies. For example, one study, looking at solid alumina and calcite particles compared to sulfur-based aerosols, found they produced significantly lower heating in the lower stratosphere and were very effective at cooling, but they might be needed in greater quantities. There are, unfortunately, still a lot of unknowns regarding the efficiency of potential candidates. A good candidate should be efficient at reflecting solar radiation, but absorb as little terrestrial radiation as possible. As they will eventually be returned to Earth, they need to be non-toxic. Their chemistry should be as unreactive as possible to avoid unintentional impacts to stratospheric ozone. And if your first thought on hearing that the list of possible candidates was diamond, wouldn't that be very expensive? Then you've already recognised that a good candidate also needs to be cost-effective. The scenarios. When talking about stratospheric aerosol injection, it can be tempting to talk in very black and white terms. That we either use it and other geoengineering techniques to fix climate change, or we do the hard work and actually drop fossil fuel emissions to net zero. The thing is, a combination of these strategies is actually possible and could theoretically result in better outcomes than either used independently. There are a lot of possible scenarios, but to simplify things, let's look at the 3 scenarios discussed in the World Meteorological Organization, WMO's, Scientific Assessment of Ozone Depletion from 2022. The 2026 report is yet to be released. These scenarios represent the results of the most comprehensive large-scale or multi-model studies. They assume that sulfur dioxide is the aerosol injected and that it is injected at or near the equator, at altitudes roughly between 18 and 24 kilometres. I'm putting the relevant figure on screen now. It's a tad detailed, so I'll be talking you through it as we go. We'll be looking at them slightly out of order because I want to explain the best case scenario last. Subplots A to C show, for each scenario, time in decades plotted against global surface temperatures, while subplot D plots time in decades against injection amount for the three scenarios. The first scenario I want to talk about is the strong SAI scenario, which is subplot B. This scenario assumes high projected emissions of greenhouse gases and explores how much SAI would be required to achieve stabilization temperatures. This scenario assumes that there is no strong effort to mitigate the release of CO2 or remove it from the atmosphere. In order to achieve and maintain the stabilization temperature, the grey dotted line in the figure, the strong SAI scenario requires increasing sulfur injections between 2020 and 2100. In this scenario, we are locked in to an endless, ever-increasing cycle of injecting aerosols, and as the sulfur dioxide injections will need to be increasing with time, the risks from any termination and, of course, the side effects will also increase over time. In the figure, this is shown by the grey arrow of global temperature increasing and only being kept in check by the ever-lengthening blue arrows representing the cooling from SAI. But what if we do achieve some moderate mitigation of climate change? How much SAI would be needed then? This is shown in the medium SAI scenario, which is subplot C. As with the strong SAI scenario, the medium scenario is able to prevent high-end global warming, but it accepts that there will be some. Instead of aiming for the stabilization temperature, here the SAI only needs to cool enough to reach the target temperature of moderate greenhouse gas emission scenario, which is represented by the red arrow on the subplot. This would require less aerosols be injected, but would still be a long-term, possibly indefinite commitment and would, over time, require increasing amounts of aerosols. The side effects of this scenario would be less than for a strong SAI scenario, but it would still lead to moderate global warming. The best case scenario here is the peak shaving scenario, which is subplot A. This is where we gain the best of both worlds, at least hypothetically. In this scenario, SAI prevents a dangerous overshoot of global mean surface temperature, thereby avoiding the worst impacts of climate change. However, unlike the strong SAI scenario, with peak shaving, the use of SAI is a temporary measure and is combined with aggressive mitigation and removal of CO2. This means that instead of needing a continually increasing quantity of aerosol injections, SAI's contribution is first increased, then gradually decreased. If you look at subplot A, the orange line represents global temperatures without SAI under this scenario, and the blue arrows under it show how much cooling SAI is providing in order to reach the stabilization temperature. In this scenario, SAI would be phased in and gradually phased out. While this would take decades or even centuries to achieve, it would also avoid permanently locking humans into an ever-increasing SAI cycle. The case against. One of the major risks of stratospheric aerosol injection is that once it begins, you cannot easily or quickly stop it. A sudden stop would mean that, within a matter of years, all the heating that had been mitigated will come roaring back. Climate change right now is bad, but a termination shock where SAI is terminated suddenly could result in extremely rapid warming at rates that would be far beyond the ability to adapt for many ecosystems and species. A slower ramp down or a quick continuation of the effort could potentially avoid these risks, but the fact remains that once you start, you are locked in for generations. Sulfur-based aerosols will also contribute to ozone depletion. They do this directly as they provide additional surface area for chemical reactions that activate halogens, which results in an increase in catalytic ozone destruction. They also damage ozone indirectly, as by heating the lower tropical stratosphere, they in turn cause changes in circulation and stratospheric transport, and increases in stratospheric water vapour, both of which impact stratospheric ozone. While the exact best locations for SAI to take place are still being researched, it would be important to avoid uneven application between hemispheres. If SAI is applied unevenly, or only in one hemisphere, this could result in a cooling gradient across the equator, which would, among other things, have serious knock-on effects for rainfall. Impacts on the hydrological cycle could be serious, even without uneven hemispheric cooling. Observations after volcanic eruptions saw weakening of the hydrological cycle. This means that SAI, particularly using strongly absorbing aerosols, could result in lower rainfall and a weakening of the monsoon precipitation in some areas, though these results depend on the type of SAI used and how it is used. SAI using sulfate aerosols can weaken storm tracks and impact both tropospheric circulation and regional climate. For example, they may result in warmer Eurasian winters, increased rainfall for northern Europe, but decreased rainfall in southern Europe. anyone my age or older, when hearing sulfur dioxide and atmosphere, probably immediately thought acid rain. What goes up must come down, and sulfate aerosols in the stratosphere will at some point return to Earth and will increase the acidity of precipitation. In already polluted areas, this effect may be minimal, but in pristine areas, such as at high latitudes, the effect may be more pronounced and harmful. Another concern is that by providing a plan B, we may inadvertently disincentivize efforts towards preventing climate change. The argument goes that people will think it's fine, we don't need to do anything to prevent climate change, we can just geoengineer our way out of the problem. There's no easy answer to this concern, though in the scenario section I discuss how this does not need to be an either-or situation. Most of the downsides of SAI can be mitigated by using alternative aerosols, but research into their effects is still ongoing. Ultimately, the biggest con here is that there are so many unknowns. Atmospheric chemistry and dynamics are extremely complex, and much more research is needed to better understand the risks here. Such research may also provide us with some options for mitigating or avoiding those risks entirely, but at present we just don't know. The case in favour. Stratospheric aerosol injection carries a number of risks and unknowns. So why is it being so intensively investigated? Well, to understand that, you need to understand what a tipping point is. A tipping point refers to a point of no return for nature. While it may be possible to reverse global temperature increases, and perhaps even return the Earth's climate to pre-industrial conditions, there are certain systems that, if disrupted or destroyed, cannot be restored. Some of the big tipping points are the collapse of the Atlantic Ocean currents, the melting of the ice sheets, the deaths of warm water coral reefs, and the end of the Amazon rainforest. If any of these things happen, there is no putting the genie back in the bottle. Which is why, with the rate of climate change and the frustratingly slow pace of efforts to tackle climate change, there is an argument in favour of geoengineering. That we may be either out of time or close to it to prevent certain tipping points, and that the only way to do so would be geoengineering. Exact estimates vary significantly between studies, but if you're asking my personal opinion, I feel that the window for fixing things may still be open, but is closing rapidly. Besides much-needed global cooling, SAI could have a number of other positive benefits. One of them is impact on vegetation, both wild and crops. Heat stress is becoming an increasing concern for plants, and SAI could reduce that. Combined with the fertilization effect of increased CO2 concentrations, this could reduce some of the negative effects of climate change on vegetation. As with basically every detail of SAI, the exact magnitude of the effect is contested, as SAI remains a theoretical technology for the time being. SAI couldn't reverse ocean acidification, as this is more influenced by high CO2 concentrations. However, ocean processes that are more strongly dependent on temperature, such as coral bleaching, could potentially be somewhat mitigated by SAI. Another ocean process highly affected by temperature is sea level rise, which could also be substantially reduced by the use of SAI. That said, ocean temperatures are complicated, and preventing surface temperature rises would not completely offset heat uptake from the deep ocean. Though heavily dependent on the location of the aerosol injection and the type of aerosol used, SAI could theoretically also reduce harmful UV reaching the Earth by reflecting it back into space. Of course, since some forms of SAI risk increasing ozone destruction, and ozone is responsible for filtering out a lot of harmful UV radiation, care would need to be taken to avoid that. Geopolitical and legal challenges. Now, this channel is dedicated to environmental science, so I try to keep discussions of things like geopolitics to a minimum. But the reality is that there is a large overlap between environmental science and politics. It's all well and good discussing whether something is technically feasible, but if we ignore the legal and geopolitical challenges, then we miss a large chunk of the geoengineering discussion. I will note up front, I am not a lawyer, so my discussion here is on generalities and the existing laws and conventions as I understand them. I've included articles in the description, or pinned comment, that get into the nitty-gritty of the legal details. That said, there are a few legal conventions that might be applied to any large-scale attempts to alter weather or climate. The most relevant is the 1976 Convention on the Prohibition of Military or any hostile use of environmental modification techniques. This, of course, applies to military or hostile uses of these techniques, but well, let's use a little thought experiment to play this one out. So country A decides that they must do something to prevent irrevocable harm from climate change, and begins a massive SAI campaign. Country B, on the other hand, is concerned about the negative side effects of such a campaign, and believes that those side effects pose such a significant danger to country B that this constitutes a hostile application of the technology. Would that work? I don't know, but I would be surprised if that or similar arguments were not used in any legal challenge from such a scenario. All that said, at present there does not appear to be any comprehensive or enforceable international framework, convention or law that covers the testing or deployment of geoengineering techniques such as SAI, which is going to prove to be a problem if or when any country decides to give SAI a serious try. Because regardless of what injection method or aerosol is used, SAI will need to be done regularly, for probably decades or even centuries. It is unlikely that whatever locations are picked, that they will all be within one nation's sovereign airspace. So cooperation between multiple countries will be required. As SAI would impact every nation on Earth, and the impacts would not necessarily be equal, some countries would be impacted disproportionately to others. And given the divisions that currently exist between the world's great powers, it is currently hard to imagine the US, China, and Russia coming together and agreeing on something like this, let alone the large numbers of other countries in the world. That's of course assuming that only nation-states would be willing or able to begin SAI at scale. An increasing number of private companies have begun work on SAI projects, and many of those lack the oversight, regulations, and restrictions present for, say, academic institutions. As SAI would need to be continued for decades, or longer, this also raises the concern of intergenerational equity, as once we begin SAI, it would be committing future generations to a path they had no say in. Arguably, this is what has already happened with man-made climate change, and we need to be mindful of the legacy and responsibility we leave to future generations. Conclusion. That was a lot to take in, I'm sure. But I would say that one thing is clear. We are now transitioning from a time of can we into a time of should we. There are still a lot of unknowns with SAI, and while the technology holds great promise, it also holds great risks and challenges. If you want my personal opinion on the topic, I take the view that, given the pace of progress towards net zero and the rate of climate change, I feel that some level of geoengineering technology or combination of technologies will be necessary if we are to avoid the most catastrophic futures. That said, with the current unknowns and the known risks associated with SAI, I would be very cautious about advocating in favour of it at this time. But as it may be the most effective geoengineering technology we have, it would be unwise to ignore its potential. Much more research will be needed, because I fear that, in the not-too-distant future, humanity will need to make some difficult choices. And the better we understand our potential options, the greater our chance of a successful outcome. I hope you enjoyed learning about this topic. Last time I covered geoengineering, the video wasn't particularly popular, but I've long since given up trying to figure out what the YouTube algorithm will decide to promote and what will prove popular. So I'm just making videos on what I think is interesting and important information, and hoping my viewers enjoy it. If you did, please let that mercurial algorithm know by liking, commenting, subscribing, and sharing the video with anyone you think might find it interesting. As always, I've left a library of links in the description, and possibly pinned comment if the description ran out of room. So until next time, thank you for watching.